We're going to introduce what we call an objective function, this function that we're trying to maximize or minimize or put together, optimize. And then what we're going to do, and it turns out that in this linear programming problem, the optimal solution will occur. If one exists, it's going to occur at one of those corner points. And the way that we find the solution is we plug all the corner points into the objective function and evaluate them and decide, well, what gives us the largest objective function value, or which one gives us the smallest, depending upon whether we're looking for the max or the min. But here is the process. Introduce the variables. A lot of times those will be given to you. This is an applied problem. So you have to define all the variables that you use. In this chapter, since we're graphing, we only have 2 variables. When we do use the simplex program to solve linear programming problems in the next chapter, we can have more than 1 variable. Okay, it says, you know, if you want, you can draw a table, and I'll generally on word problems draw a table as well. Determine the objective function, there it is, and then write the linear objective function. Determine what it is that you're trying to maximize or minimize, and then write an equation. It's not an inequality this time. The constraints are the inequalities. So write down all the inequalities in the problem. And then where it says write the non-negative constraints, that means x is greater than or equal to 0 and y is greater than or equal to 0. Most of our application problems will be such that you're going to be looking for a positive value of x and a positive value for y. Okay, the objective function is generally going to be given. You'll see here in a second what it is. And it's going to look something like this. It's going to be linear, so it's going to be something x plus something y. And the objective function variable we're going to use is z. And then here's the big result of this section. It's called the fundamental theorem of linear programming. The optimal value of the objective function, and you read optimal as maximum or minimum. Value of the objective function in a linear programming problem, if it exists, the value must occur at one or more of the corner points. And so what we're going to do is begin just like we did your problems. We're going to graph the inequality. We're going to identify the corner points. And this says, let's put them in a table so that we can keep everything organized. All right, so let's take a look at how they ask a couple of the questions. It says here, in these problems here, the feasible region is a set of points on and inside the rectangle with vertices. Okay, so what they're saying is that those 4 numbers right there are corner points. And then it says find the maximum and the minimum values of the objective function Q over the feasible region. So this is where we're going to introduce this corner point table. So it's going to look something like this. Corner point. All right, I'm going to go in way more detail than you need to, but we have 0, 0, and 12, 0, and 0, 5, and 12, 5. The x value is the x coordinate, and the y coordinate is the second coordinate. So if you like, you can break them up this way. All right, and now I'm just going to choose one of these, and I'm going to choose number 2 to do. In number 2, Q, which is this is the objective function. Notice it's an equality. It doesn't have any inequalities in it. Is equal to 3 times the x value plus 15 times the y value. All right, so in this one, Q is equal to 3 times 0 plus 15 times 0. That's 0 plus 0 or 0. In the next one, the x value is 12. So we have 3 times 12 plus 15 times 0, and that's 36. So we're plugging the x and the y into the x and the y in our objective function. This is the function we're trying to maximize or minimize. This one we have q is equal to 3 times 0 plus 15 times 5, and that's 75. And finally, we have 3 times 12 plus 15 times 5. 75 and 36. What is that? 111? Now we know that the maximum and the minimum will occur at a corner point. So once you have this table done, then you just go by inspection and look at all the values that are possible values of Q, our objective value. The smallest one is 0. This is the minimum. And of those 4 numbers, 111 is the largest of the 4, so that is the maximum. Okay, and I think we've done pieces of all the pieces of the linear programming problem in 2 dimensions. So let's look at an entire problem from start to finish. Is that what they're going to do here? All right. Let's take a look at a problem like, I don't know, number 14 here. This is the same thing as the previous problem, but they give you the graphical representation of the region as opposed to just telling you where the corner points are. But you really do it in the same way. I would recommend strongly that you do the corner point table. A lot of times what I'll do is just identify the corner point and then write the value of z on each one of the points. But in this case, there are 5 different corner points, so you have to put all 5 into your objective function. Okay, so here's how you can determine where it's going to be. What you want to do is you want to have a slope. If c is some constant and you tried to figure out the slope of this line and you solve for y, well, it's going to be -7/9 is going to be the slope of this line. So if you put a straight edge in there so that it has a slope of -7/9, all right, so like 0, 0, and then rise is 7, at the same time run is 9. It's going to look something like that. So imagine that this is a line with slope -7/9. Now we're going to take it and we're going to just go right through the region. And where you enter the region, that's where the minimum is going to be. So without actually even calculating, the minimum is probably going to be right there. If I continue that slope up, the last point that we exit from our shaded region, that's going to be the max. And the last point we exit is right here. So this is going to be the max. That's going to be where the max occurs. We still need to calculate. So let's do the table. We have corner point. And if you like, you don't have to really do this, but break it up into the x and the y. And then we're going to evaluate c here. We use c a lot because a lot of times what we're trying to minimize in our financial applications are the cost. We're trying to minimize the cost. All right, I'm just going to go around here. 0, 15, 0, 8, 4, 3, 15, 0, and 15, 15. Break apart the point into its x and y components, and then evaluate c in each case. 7 times 0 plus 9 times 15, that's 135. 7 times 0 plus 9 times 8, that's 72. 7 times 4 plus 9 times 3, 27 and 28, that's at 55. 7 times 15 plus 9 times 0 equals 105. And finally, 7 times 15 plus 9 times 15 is equal to 240. All right, so this is the last step. Again, you can see here, the smallest value is 55. So we would say the min equals 55 at the point 43. And the largest is down here. The max is 240, and it occurs at the point 15, 15. So they're going to want all three of those numbers. They're going to want the maximum or minimum value, and they're going to want to know the place where it occurs, the x and the y coordinate where it occurs. So this is the last step. Okay, now we're going to put it all together. And we'll do a problem. When you see this notation here, they're saying x and y are both greater than or equal to 0. So that's the same thing as x is greater than or equal to 0 and y is greater than or equal to 0. These are the ones that are called the non-negative constraints. So this is a constraint, and these two are constraints. And the one with the equal sign, this is the objective function. This is the thing we're trying to minimize or maximize. And in this case, they're specific. They want us to minimize. They don't care about maximizing here. So we're going to minimize. C equals 15x plus 25y, subject to the constraints 4x plus 7y greater than or equal to 28 with x greater than or equal to 0 and y greater than or equal to 0. All right, so that's another way to write it. You can see how they wrote it there. All right, the objective function is going to come last. That's the only time we use that is at the end of the problem after we have identified the corner points. The first part of this is a problem like what we did last time, systems of equations. Now, instead of drawing the whole axis like this, negative 10 to 10, negative 10 to 10, we know that we're in the first quadrant. So what I typically do is just draw an enlarged first quadrant and just ignore all this over here. Because we have x greater than or equal to 0, and we have y greater than or equal to 0. So this tells us that we're in the first quadrant, where x and y are both positive. And luckily they gave us a nice line here. Remember, we're going to replace the inequality symbol with an equal. These are always going to be lines in this section. If you let x be 0, y is 4. And if you let y be 0, x is 7. So just using the intercept method here, it's pretty, not too bad to determine 2 points on that line. And that's really all we need are the 2 points. 0, 4, 1, 2, 3, 4. There it is. And then 2, 3, 4, 5, 6, 7. There. And then we're going to connect them together. And a line. I always label the lines, and you're going to want to also, because especially in those problems that have multiple lines in them, to find corner points, you have to identify the 2 lines that meet together to create a corner point. And so you want them labeled so you can do that pretty easily. All right, so the question now becomes, are we down in this triangular region, or are we above up here? So let's check a point, 0, 0. 4 times 0 plus 7 times 0 is 0. Is 0 greater than 28? Here's my test. And the 0, 0 we determine is not a solution. So we don't want to shade 0, 0. And that means that we don't want to shade anything on the same side of 0. So that means we're going to shade everything the other side. So we're going to shade above this line. And if you put those three shadings together, here's your region. Oops, don't want to dip below that line. So just follow the bounded area, and it's unbounded up here. And if you just go all the way around the region, there's a corner point. Not only is that a corner point, it's an easy one to determine because it's right on the x-axis. And it was actually a point that we used to graph our line. 7, 0. Come up here. Here's another easy one to figure out because it also is a point. And those two are it. That's it. Those are the only two corner points. If there is a maximum, and there is no maximum here because of this unbounded region, just think about this. All this region is up here. So like 100, 100, 100, 100 would be up here. If you plug 100 and 100 there, you get a very large C. But that's not going to be the largest C because you could also plug in 1,000, 1,000, and 1,000,000, 1,000,000. And since the region is unbounded, we're going to have no max. And maybe that's why in this problem, they said find the minimum. They're not interested in the max here. Well, it just so happens that our 2 points here are the only 2 corner points. So I'm just going to add another column. If here are 2 corner points, and then I'm going to evaluate C. 15 times 0 plus 25 times 4, and that is 100. 15 times 7 plus 25 times 0, and that is 105. And those are the only 2 candidates to be the minimum. And of those, 100 is smaller than 105. So our conclusion is the minimum is equal to 100. It occurs when x is equal to 0 and y is equal to 4. So that's a complete problem. And they will get more complicated because you're going to throw more lines than just one inequality in there. And some of them are going to be so, they're going to be very compact together, so it's going to be difficult to see where the intersection is. Okay, let's take a look at number 32 and see what we got here. I mean, it would be nice for me to do one of every kind of these homework problems, but I want to give you just the gist, and then in the lecture notes, I'll do a couple more problems so you have some more to draw from. But let's take a look at number 32. Here, in this one, they want us to do both, minimize and maximize. And because they want minimum and maximum, probably this region is going to be a bounded region. Notice that the objective function here has a negative x in it. When we do real world problems, word problems, both of these coefficients are going to be positive. All right, so you're going to be fast at doing these or slow depending upon how well you can graph these intersections. And the graphing calculator can be your help here, especially when you're finding points of intersection. All right, so this is 32. We're going to maximize and minimize this objective function. And then our constraints are these. And then we have what we call the non-negative constraints. X greater than or equal to 0, y greater than or equal to 0. So again, we're in the first quadrant, and that'll help us a lot as we go and graph this feasible region here. All right, I have everything I need. I'm going to draw a big. If you want, you can go check this out on Wolfram Alpha to see what it gives you. It probably does a much better job with bounded regions than it does with unbounded regions. I think I'm going to put 6 up here. And here's the line y equals 6. So I'm going to start with this one here first. And since we're looking for all values less than 6, all the y values that are less than 6 would be shaded. So we're going to shade down underneath this horizontal line that has the equation y equals 6. We also know that we're in the first quadrant, So greater than 0 on the x-axis and x equals 0 is this vertical line. Y equals 0 is this horizontal line. All right, so now we've got this region here. All right, so these three are graphed. Now let's go to this one. 2x minus y is equal to 4. And I like to plot intercepts because they're so easy. When x is 0, this whole term goes away. So to make the statement true, y would have to be -4. And when y is 0, x would be 2. All right, now you can't see it very well, but here's my -4, and here's 2. So I'm going to draw a line coming up here. And then I'll extend it. There it is. And here is my 2x minus y equals 4. Every time I draw a line, I'm going to label it. All right, I want to check this point right here, 0, 0, in this inequality. 0 minus 0, is that greater than 4? And the answer is no, it is not. So we're not going to shade 0, 0 here. That means we're going to shade everything under 0, 0. So we don't want to shade up here because we don't want to hit 0, 0. So we're going to shade everything else. All right, so now you can see that this inequality here, x greater than or equal to 0, does nothing for us because now we know we're in this region here. All right, the last one that we're going to graph is the line that corresponds to -x plus 2y is less than or equal to 4. We're going to replace the inequality symbol with an equal sign, plot a couple of points. When x is -4, y is 0, and when x is 0, y is 2. All right, unfortunately, I don't have my -4 over there to the left, so I'm going to try another, a different point. So maybe I'll try the point when x is 2. Do I want to? Yeah. When x is 2, y would be 3. Okay, so if x is 2, then we've got -2. If y is 3, we have 2 times 3, 6. 6 and -2 add up to 4. So 2, 3 is a point that is in my the region that I'm interested in. All right, so I'm going to plot 0, 2, which is about right here. And then I'm going to plot 2, 3, kind of right in the middle. And if that line extended off to the left there, you would see that it does in fact hit -4. All right, so there it is. And let me label it. -x plus 2y equals 4. All right, now I need to know whether I'm going to shade above this line or below. 0, 0 is below the line, so I'm going to check 0, 0 in this inequality here. 0 plus 0 is less than 4 is true. So in this case, I do want to shade underneath this line. All right, I will extend my y equals 6. So you can kind of see where the shaded region is developing here. And so it's going to be all of this. It's going to stay above 0 and below 6, but then it's also altered by, and extend my y equals 0 here. So all of that region. I thought it was going to be bounded, but turns out that it's not. It could, however, still have a max and a min. Let's check it out. So we need to find this point. This point's not too bad because it was one of the points, it's right on the x-axis. And we know the coordinates of that point. So that point right there is the point 2, 0. No other corner points over here. So there's one, and we got to find this one. And we continue, here's another one. but I know what the y-coordinate of this point is. The y-coordinate is 6 because it sits on the line y equals 6. All right, so the first thing we'll do is find this corner point. This corner point is where negative x plus 2y equals 4 intersects with 2x minus y equals 4. So that's why I label them, because I can see which two lines we need to put together. So I'll multiply the top equation by 2. So I get negative 2x plus 4y equals 8. And by multiplying this x by 2, I create a negative 2 that I can add to the 2x that will lead for the x coordinates to cancel out. So add 0, add 3y, add 12. So the y coordinate is 4. And if the y coordinate is 4, I'm going to replace the y coordinate with 4, and I will get the x coordinate is also 4. So that point right there is 4, 4. And you can check it out. It works in both of those two equations. We already know that the y coordinate is 6 to this point. So we know that that point is where y equals 6 and then this line right here intersect. So I'm going to take negative x plus 2y equals 4, and I know that y is equal to 6. So this will enable me to solve for x. Okay, so you have to do all the algebra correctly, but and you can see that my graph is not quite drawn to scale, as it was drawn freehand without graph paper. But the x coordinate is 8, so our final corner point there is 8, 6. So we have 1, 2, 3 corner points. I'm going to put them in a table. I'll do that work down here. And then our objective function is p, negative x plus 3y. So I'm going to evaluate each and then consider, you know, is the max and the min present, or is there a max but no min, or is there a min but no max? Here are the corner points: 0, 2, 0, 4, 4, and 8, 6. So for the first one, when x is equal to 2, at the same time y is equal to 0, we get negative 2. When both the x and the y are equal to 4, 12 minus 4 is 8. And then negative 8 plus 3 times 6, 18, minus 8 is 10. So the candidate for the min would be negative 2, and the candidate for the max would be 10. But this is an unbounded region. So we probably should check to make sure that these are in fact the max and the min. Okay, really what you can do is you can just, you know, run around the feasible region here. By the way, this is all the feasible region. Trying to familiarize you with some of the terms that they're going to be using in this section. The shaded region is the feasible region. These are the feasible solutions. I can already tell that, say, this point right here, and let's say that it's 8, 0. That's part of this solution. The feasible region is part of the region, 8, 0. And when I put 8, 0 in here, notice the x coordinate is negative. So if I put in 8, 0, I'm going to get negative 2. Negative 2 is less than, or negative 8 is less than negative 2. So this can't be the min. There's something bigger than the min. In fact, if you go along this horizontal line here in our feasible region, where the y coordinate is 0, the x can be as large as you want. And when we put a negative in front of the x as large as we want, and then keep the y at 0, the further we go out along this line right here, the more and more negative we're going to become. So negative 2 was our only candidate for a min. it turns out that there are other points that would give us something smaller in that feasible region. So what we're going to say here is that we have no minimum. We should check the max. Is there anything that would give us something more than 10? You can check a couple of points. Let me do the slope of the line argument here. So let's take this guy here and just choose any old number for p. If you just want to leave it p, you can solve this equation here, this objective function for y, but p is supposed to be a constant, so you can just think of this as the y-intercept. And then you have 1/3 x. So I'm going to draw the line with my ruler of y equals 1/3 x. So that's a rise of 1 and a run of 3. So this would be a negative slope. We want a positive slope. And you know that the slope here is 1/2. It's a little steeper than 1/3. And this one here has a slope of 1/2, which is a little steeper than 1/3. So our slope is going to come like this. All right. So where we enter this region is going to be right there at that point. The next point it hits is here, but the first point it enters is where the max is. And as we scroll down and just keep going through this, the further we go to the left, the further we're going. We're never going to exit this region. If you just go right through the region, you're never going to exit it with a slope of 1/3. This slope here is 1/2, so we know 1/3 is a little bit less than that. Hits there first, and it's never going to exit the region. So no min, but the max is here. Bounded regions are much nicer. All right, I don't know that I can do anything new with the rest of them. You know, you can see you're going to get some decimal coefficients that makes them a little harder. Sometimes you're going to have 3 inequalities instead of just 2. But I think what I'd like to do now is to end with one of the word problems so you can see how these are constructed. All right. It's going to take a lot of practice to figure out where you pick out the constraints and where you pick out the objective function. But just remember that generally you're always in these word problems going to have these non-negative constraints. Those are going to be 2 of the constraints. You're going to have some other constraints. Constraints are inequalities. You have to be able to figure that out. And then you have to figure out the objective function. Now, the objective function is something that you're trying to maximize or minimize. So as you're reading the problem, try to identify this thing that you're trying to find the largest of or the smallest of. What is the cost for this amount of food? What's the next? How many ounces of each food should be used to meet the minimum daily requirements at the least cost? So probably you want to minimize the cost. So we'll call it C equals something. Okay, so and if you go back to that application problem at the beginning, or when they told you how to do the application problems, they said, you know, it might be a good idea to draw a table. But the first thing you have to do is to identify the decision variables. In this section, since we're doing everything graphically, you're going to have 2 decision variables. So what determines the cost? All right, let's read on. It might take you 3 or 4 readings of these word problems to get all the constraints down. Lab technician is asked to formulate a diet from 2 commercially packaged food A and food B, for a group of animals, each ounce of food A. Okay, so X equals the number of ounces of food A, and Y equals the number of ounces of food B. So the first thing is to quantify the variables. Write them as numbers. so that when we find the corner point where we have a minimum cost, we're going to find the x and the y of the point that gives us the minimum cost, and those are directly the two values we're looking for to solve this problem. So define your variables as quantities, in this case, the number of ounces of food. Fat, carbohydrates, and protein. Fat, carbohydrates, and protein. So we're going to create this grid. Looks something like this, and then put a total over here. And then maybe we'll see these constraints appear right before. And there's one more. I'll put a double line here, reading on. Each ounce of food A, so now we're in the first column, contains 8 units of fat, 16 units of carbs, and 2 units of protein. And then we move over, the next sentence gives us information about food B. 4 units of fat, 32 of carbohydrates, and 8 units of protein. The minimum daily requirements are 176 units of fat. Okay, so what they're doing is that they're going to feed these animals some of food A and some of food B to give them some variety in their menu, in their food. And they know that they need at least, so over here, greater than or equal to 176 units of fat. So the 176 total is in the fat row. 1,024 units of carbs, minimum requirements. So it needs at least that many units of carbohydrates, milligrams or whatever it is the unit is. And needs at least in their diet, to be a healthy diet, 384 units, probably grams or, yeah, probably grams of protein. If food A costs 5 cents per ounce and food B costs 5 cents per ounce, how many ounces of each food should be used to meet the minimum daily requirements at the least cost? And what is that cost? So we pretty much have everything that we need here. What you're going to do is you're going to multiply each ounce of food A has 8 units of fat. And if there are X ounces of food A, then we would get the total fat by multiplying 8 times the number of ounces. And then we're going to add to that similarly for Y. And what you're going to see right from the table is you're going to generate these constraints. And you're going to have 3 of them. You're also going to have the X greater than or equal to 0, Y greater than or equal to 0. So you're going to be working in the first quadrant. Now for this last one, it's not a constraint. It's the objective function. But we do it in the same way, except we're going to say the objective function, the thing that we're trying to minimize is cost. So cost equals. They're not putting any constraint on the cost. That's the thing that they want you to minimize. And so that becomes the objective function. It would be interesting to see how Wolfram Alpha would handle this one. I mean, the thing about a nice computer algebra system like that is it can do everything just instantly, as long as you type everything in. So if you typed in the 4 constraints and the objective function, I'll bet you it would return the answer. And we can check it out. We'll do it using the graphing calculator here. And I don't know that I've shown you this before, but I'm going to enter in these equations, but I have to solve them for Y. So I need to get, for the first equation, I need to bring the 8x over and then divide by the 4 attached to the Y. In the second inequality, I start with 1024, bring over the 16y or 16x, and then I want to solve for Y, so I have to divide everything by 32. I'm not even simplifying these. Okay, in the next one, this one here, I got to bring the 2x over, so 384 minus 2x, and then I need to divide by the 8. I know that I'm in the first quadrant, and so for each of these, just so I can see it better, I'm going to do just the opposite of what they want us to do. So they want us to do greater than and shade above, but I'm going to do just the opposite and shade below, all three of them. And you just hit enter to the left of the y equals to get the inequality. I'm going to change the window so that I begin at 0 on the x and I begin at 0 on the y. This is the number of ounces of food you would feed. So, you know, it's not going to be huge, but let me just go up to 20 and see if I can capture everything with a y min and a y max of 20. 20 ounces of food? Well, if it's a horse, that might not be good enough. All right, well, let's see what happens. Okay, not big enough. Okay, so I guess it looks like the only corner points are going to be this one and then one way over here. So it was nice that we did all this work here, but we're shading above everything. Okay, so this white region up here is your feasible region. It's going to come down, go down here, hit the x-axis, way over here, and then go flat over there. So there's going to be a corner point here and a corner point there, and those are the only 2 points that are candidates for minimizing the cost. And it looks like we're going to buy just either food A or food B, but not both.